Welcome to the online version of linear algebra. This is going to be our format for the rest of this semester, and please excuse any awkwardness that I may have. This is my first time recording lectures, and so I'm very new to this. Hopefully I'll get better as we go, but if I have any pauses, awkward pauses, or anything like that, please excuse them. I've tried to record this enough times already. I need to just go. In this lecture, we will be covering section 3.6, and as you may have noticed, there are going to be multiple videos for this section. I broke it up into multiple parts. Hopefully that will be helpful to you guys because you might have questions, you might want to review part of the lecture. This is definitely one of the advantages of having online lectures, doing videos and that kind of stuff. So I do encourage that you take advantage of that. Now, I would normally ask if there's any questions at this point, but because we're doing videos, that's not possible. If you do have any questions over the material, you can either email me as normal, or I will have office hours every Monday, Wednesday, and Friday during our old class time of 11:30. There's a link on Blackboard that's just labeled office hours that'll allow you to join a meeting through the Zoom application. You will want to make sure you check out that link early to make sure that if there's any Zoom software that you need to install, that you have done so before the office hours actually begin. Alright, hopefully there's no other questions about that kind of stuff, and we can actually get on to the mathematics of all this. In 3.6, we are going to talk about various ways to obtain subspaces of Rn from a particular matrix. So we've been talking about vector spaces, but now and subspaces, but now we are actually going to take a step back and look at matrices again and see what subspaces are associated with any given m by n matrix. Now, as you can see on the screen, we have already seen a way of doing so, the so-called null space of a matrix. We saw this back in 3.2. And it's simply all the vectors that if you multiply that vector by that matrix, you get the zero vector. And we prove that this is actually a subspace of Rn. And this will actually be relevant to some of the things that we're going to be talking about today, but we're not going to focus specifically on this one. What we are going to focus on are what we call the row and column spaces of our matrix A. These are R1 by n, subspaces of R1 by n and a subspace of Rm for a given m by n matrix. But before we even get started, I'm going to kind of change what the book does, because usually people do not talk about R1 by n. Those are, when we have those, we're talking about something of the form of a vector in R1 by n. That's a vector of the form, say, 1, 2, 3, just a row like that. But because of the way we actually usually talk about Rn, we usually want to actually think about this as not the row vector 1, 2, 3, but instead the transpose of that. So instead, the column vector 1, 2, 3. And while the book actually will insist that the row space is a collection, is a subspace of row vectors of the first form, usually people will use the transpose, the column vectors instead. It's just a little bit more convenient. But you can use either one. I won't be too picky about that. So what is let's give an example of a row space and a column space. So let's say we have a matrix A, and I'm going to make this the matrix 5, 3, negative 4, then 8, 5, 2. This is a 2 by 3 matrix. Its row space is either a subspace of R1 by 3, or you can say it's a subspace of R3. Its column space is a subspace of R2. And what we're basically doing for the row space, I'm just going to put row equals, this is going to be a span of vectors. It's the span of the vectors that are the rows of A. So the first row of A is 5, 3, -4, written as a column vector. And then the second row is 8, 5, 2. So we're talking about all the vectors in R3 that are a linear combination of these two vectors. Now that may actually be a two-dimensional subspace, or it may actually be a one-dimensional subspace. We might have to determine that later on. So in this particular case, it looks like it's going to be two-dimensional. The column space, on the other hand, now we're just taking the span of the column vectors. So the first column is 5, 8. The second column is 3, 5. And then we have a third column of -4, 2. I'm kind of going off the page. I'm sorry about that. Now, this looks like it is a three-dimensional space because it is spanned by three vectors, but it is a subspace of R2, so, well, it's going to have to be at most 2 dimensions. It can't be bigger than the dimension of R2. So obviously one of these vectors is kind of unnecessary. We don't actually need all these vectors, but that is our definition of what the column space is. It's the span of those vectors. But every vector in this column space is a linear combination of those three vectors. It's a little bit difficult sometimes to actually work with the row and column space using the vectors that you just see in the matrix. So one thing that we like to do is actually reduce it to a little bit better of a basis, or at least try to find out a better basis for our row and column space. Now that's a little easier to do with the row space because we have this convenient theorem, theorem 3.6.1. If we have two row equivalent matrices, then they have the same row space. That means that if we take a matrix, if we start with, say, our matrix A from the previous page, and we do Gaussian elimination, we will get whatever we get from that will still have the same row space. We will not change the row space by doing our row operations. And remember what our row operations are. We are allowed to swap two rows. We're allowed to multiply a row by a non-zero number. We're allowed to add a multiple of one row to another row. And really the main important thing to note there is in the second row operation, we specifically cannot multiply by 0. That would actually change what our row space is. But as you can probably tell, swapping two rows really doesn't change how the span works. Adding a multiple of one row to another actually just gives you another vector in the same space. And so that doesn't actually change anything. It's as long as we do not multiply one of the rows by 0, we haven't actually changed anything from having linear combinations in the same space that still span the same row space. And you can go through the proof of this. I have it presented. We're not going to focus too much on that. But the main thing is that what we are going to do in order to talk about the row space is that we will usually take our matrix and we will go ahead and put it into row echelon form. So let's go ahead and take a matrix. I'm going to take something that's similar to what we had before, but I do want it to be a little bit bigger. So I'm going to take matrix A will have the same 5, 3, -4, and then 8, 5, 2. But I'm going to have a third row of 3, 2, 6. If I take that matrix and I go through all the steps of Gaussian elimination, I'm going to get another row echelon form matrix U. I'm not going to go through these steps. We'll have more examples of this in the examples video. So I'll start with an example there and I'll work through all the steps. But I just want to do a quick example right here. If we do all that, we'll get the first row is 1, 3 over 5, negative 4 over 5. Some fun fractions in there. Then we'll have 0, which we have to have for row echelon form. 1, again, for row echelon form. This one actually turns out to be 42. And then we actually get a row of all zeros. So what we can see here is if we take the row space of A, so again, I'm just going to put row just to be a little shorthand for that. The row space of A would have been 5, 8, the span of row 5, 8, 3, sorry about that. Yeah, rows, not columns, sorry. 5, 3, negative 4, 8, 5, 2, and then 3, 2, 6, which on its face looks like we have a three-dimensional space, that we actually will span all of R3. But since A and U have to have the same row space, we can actually see that the row space is in fact also spanned by a different basis, it will be a basis, but a different collection of vectors that are given as 1, that negative sign, 1 3/5, negative 4/5, and then 0, 1, 42. We don't have to include the row of all zeros because that's not going to contribute anything to any linear combinations anyways. So in fact, the row space of A is actually spanned by only 2 vectors. And you could go through, and because we're talking about row echelon form, those vectors are actually going to be linear independent. So in fact, the row space of A is in fact two-dimensional. And we're going to give a name to what that dimension is. If we can determine the dimension of the row space of a matrix, we are going to call that the rank of the matrix. And the book denotes it in the form RA in K of A. Some people will write this as just RK of A. It's an important number about a matrix that will determine a lot about it. And we'll be talking about this throughout the course of this section, and we'll probably come back to it again in the future as well. It will have an effect on what the matrix A does in various situations, especially when we start talking about linear functions in the next chapter. Another thing that I will note here is that we could have called this the row rank and talked about an equivalent column rank as the dimension of the column space. That actually is not important to do. We don't need to do that, and we'll talk about that in the theorems video for this section. We'll talk about why we don't need to do that. Finally, let's give a theorem about the column space. So we've been talking about a lot about the row space, that we can actually do a lot with the row space by doing Gaussian elimination. Because we're doing row operations, that only works with the row space. It doesn't work with the column space, though there is some information that we will get about the column space by doing Gaussian elimination. We'll talk about that again in the examples video. But one important theorem that we want to talk about is this consistency theorem, as the book puts it. Remember back in section 1.3, so this is a ways back, we had this theorem that said a linear system AX equals B is consistent if and only if B can be written as a linear combination of the column vectors of A. Well, that's exactly what the column space is. It's the collection of all linear combinations of the column vectors. So we are going to rephrase that theorem in terms of the column space, that a linear system AX equals B is consistent if and only if B is in the column space of A. This is an important result about what the column space really is. It's the collection of all vectors that actually do give you a consistent linear system if you set up as AX equals B. Alright, so that'll be it for our definitions for now. We will talk about some theorems coming up, but at first I do want to go through some examples of how you might do some of this kind of stuff. Find out what the row space is, and maybe going through some Gaussian elimination, and probably do some stuff with the column space. Find out a good basis for a column space of a matrix, and then we'll get some good examples of the kind of stuff. But I'll see you guys in the next video. Make sure to watch all of these videos so you can know exactly what's going on. And if you do need to come back and re-watch a video, please do so. That'll be important so that you can actually stay up on all this stuff. So I'll see you guys later.